Okay. Good evening to everyone. I think last class, please check this. I will share the slides. Last class, we started a relation. Okay. So I think the last class, at the end of the class, we discussed this concept. I think so. The composition of relation. I told the difference between um the two notations. One is from Venkatraman book. Venkatraman book, again I'll tell. I think maybe because this is most important one, that's why I'll repeat again. In Venkatraman book, they will use this notation for okay for composition of function or relations, whatever it may be. So first he will apply G, and then he will apply what? F. Okay, so this is in the Venkatraman book, and that's why he's in Venkatraman book. M R composition is okay. Suppose M R composition is he will write first. He is applying MR. Okay, the S. Okay, he is applying MS, and then apply what? MR. But in the Venkat Virarajan book, he is first applying F. Okay, first he is applying F, and then he is applying what? G. So that's why he is writing MR composition S is equal to F means here R. So MR composition and then MS. So okay, so this is the main difference between the two notations. So yeah, I think you can follow. I feel that this is better. Okay, you can also follow this one. Okay, you'll get the marks in the examination. No problem. Okay, now okay. So the next problem is if R is. I think voice is uh, audible.
Yes, sir.
Okay, thank you. Three. Okay. If R is the relation on capital A is equal to 1 to 3 such that A comma B belongs to R, if and only if A plus B is equal to even number. Find the relational matrix MR. Find also the relational matrices R inverse, R bar, that is complement, R complement and R square. So this is a question. Now solutions start from here because we know A and B are related if and only what A plus B is an even number. So here we have set what 1, 2, 3. From this set, we should take the numbers from this set such that it should satisfy what A plus B is even. So 1 comma 1 is an even number, 1 comma 3 even number, 2 comma 2 okay, and then 3 comma 1 and then 3 comma 3. So this is a matrices corresponding a matrix. This is the relation R. This is the corresponding matrix for this relation. So first you should write here what? One here, 1, 2, 3, uh, row wise, column wise, 1, 2, 3 here. Okay, you should write 1 comma 1 is there, that's why 1 comma 2 is not there, 0, 1 comma 3 is here, 1. Similarly you can fill up the matrices. Next we need to find the relational matrices R inverse. So M R inverse, that is matrix representing the relation R inverse, is same as the transpose of MR. So transpose of MR means transpose of this matrix. So this row is into this column 1 0 1 here. Next to 0 1 0. Okay. Next to this third row is third column 1 0 1 1 0. So now this position again, this is 1 2 3, this is 1 2 3. So here R bar is what? R bar is a complement of, I think MR inverse. Okay, you can check it. MR inverse. I think MR inverse is same as what? Here, MR. Okay, you can check it because it's a symmetric matrix. So that's why both of them are what? Same. Both of them are same. 101, 101, 010, 010, 101. So then what is R bar here? R bar is same as what? R. You can check it. R bar is what? 1 comma 1. So here this position is 1 comma 1. So here 1 comma 1. This is what? 1 comma 3. Next to what? 2 comma 2. Next to 3 comma 1. 3 comma 3. Because MR and MR transpose are same. So R and R inverse are what? Same. Okay. Next, complement of R bar. Sorry, R bar. R bar is what? Complement of R. R bar is complement of R. So you can find directly also using matrices also. R bar from this, how to find R bar? So the element which is not in R, okay, not in R. So is what? 1 comma 1 is here, 1 comma 2 is not here, okay, 2 comma 1 is not here, 2 comma 1, and then 2 comma 3 is not here, and then 3 comma 2 is not here. So that is in whatever it is not in R, it is in what? R bar. So this is one of the way. Or M from MR you can find a MR bar. How? Replacing 1 by 0, 0 by what? 1. So 0, if it is 0 here 1 is 1. If it is 1 means what? Here 0. So okay. So which is same as the matrix obtained from MR by changing what? 0 into 1 and 1 into 0. Okay. So now I think we'll get MR bar. From this you can check R bar. R bar is what? Here 1 2 3. Here also 1 2 3. This position is what? 1 2. Okay, 1 2 is here. This position is what? 2 1. 2 1 is here. This position is 2 3. 2 3 is here. This position is 3 2. Okay, 3 2 is here. So next R square. R square means R composition R. So MR square is same as MR composition MR. So here both of them are R. Okay, so there is no. Okay, you should write again what the same matrices. So this is also MR. This is also what? MR. I think the last class I told that how to find the composition of two matrices is just like a matrix multiplication. Take this row and take this column 1 into 1. Okay, so 1 into 1 instead of 1 into 1 instead of multiplication you should use what? And. So 1 and 1 is what? 1. Okay, 1, and then we'll put a plus. Okay, plus instead of plus you'll put what? R. 0 and 0 is what? 0. Again instead of plus R. 1 and 1. 1 and 1 is 1. Next, take this row and this column. Okay, 1 and 0 is what? 0, and then instead of addition R, 0 and 1 is 0, and then R, 1 and 0 is what? 0. Similarly, you should fill up the remaining elements. So if it is at least 1 is here, so 1, because here you have R. So 1 here what? 0, here what? 1, 0, 1, 0, here what? 1, 0, here what? 1. Now you can see this is again R. So MR square is same as what? MR. So and hence it can be found that R square is equal to R composition R, which is same as what? R. Okay. So this is MR square is same as what? MR. Okay. Next problem. If R and S are be the relations on a set A represented by the matrices MR and MS. Find the matrices representing R union S, R intersection S, R composition S, and S composition R direct sum. This is called direct sum. Yes. Okay. So this is a question. Now, first matrix representing R union S means M R union S. Matrix representing R union S, M R union S, which is defined by, yesterday I told that MR join MS. So MR join MS means just matrix addition. Okay, wow. So you know how to add the two matrices. Okay, you can check the first row only. Okay, first row 1 join 1. So we'll usually what 1 plus 1, 1 plus, sorry, 0, 0 plus 0. So instead of 0 plus 0, 0 or 0. And then what? 1 or 1. And then 0 or 0. Similarly, you can write the remaining elements. So here what? 0, 1, 0, 1, 1, 1, and then 1, 0, 1, sorry, 1, 1, okay, and then 1. And then MR intersection S is MR meet. This is join. Here what? For intersection, you put meet MS. So here, instead of join, here put just meet. So 0 and 0 is what? 0. 1 and 1 is 1. 0 and 0 is what? 0. 1 and 0 is also what? 0. 1 and 1 is 1. Similarly, you can write the remaining elements. Okay, MR composition S. As per Virarajan notation, MR composition S is what? MR composition MS. But as per the Venkatraman book, MR composition S is what? MS, first you should write what? MS composition MR. But both of them are different. But anyway, okay, we need to follow any one of the notation. Better, from my point of view, we can use Venkatraman's notation. Okay, but okay, here if you want to check whether this answer is correct, we need to apply only this idea. So you know how to find the composition of two matrices. I already explained to you. It's just like a matrix multiplication of MR and what? MS. So multiply and check the answer. You can verify it. And then next, MS composition R is what? MS composition MR. So again, first you should write MS matrix MS, and then write MR. Okay, and perform the matrix multiplication. In matrix multiplication, first you will multiply and then you will add. So instead of multiplication, you should use first to here what? And then for addition here you should use what? R. Okay, last one, M direct sum, M R direct sum S is equal to, which is defined by MR union S minus MR intersection S. Okay, what is MR union S? This is MR union S. This is MR intersection S. So like subtraction, 0 minus 0, you can check 0 minus 0 is what? 0. Okay, here 0. Next, 1 minus 1. Okay, 1 minus 1 is what? 0 again. Next, 0 minus 0 is again 0. Next, here 1, here 0. Okay, 0. Actually, this is what? Union, this is intersection. Okay, so suppose here it is 0 means it should be 0 here. Okay, you can check it. These two positions are 0 means here also it is 0. So those positions are 0 only. If it is 1 here 0 means we'll get finally 1. If here also 1, here also 1 means what? There will get what? 0. So that is the idea. Okay. So last row, 1, here also 1. There you should write what? 0. 1 minus 1. Here 1 0 means 1. Here 1 0 means what? 1. So okay, 1 and 1. Okay, I think yes, maybe yes. Okay, I think we will discuss these two theorem. Okay, I will I will explain maybe the other PDF. Okay, so this is a next theorem, associative law for composition of relations. So let A, B, C, D be sets. There are 4 sets. Suppose R is a relation from A to B, S is a relation from B to C, and T is a relation from C to D. Then T composition S within bracket composition R is equal to T composition S composition R. Okay. So the main idea is to prove A equal to B. Okay. To prove A, suppose A equal to B, I want to prove. Then I want to prove A is a subset of B and B is a subset of A. If I prove these two, then we can say what A equal to B. So how to prove this one? For to prove this one, I will take some arbitrary element. Okay, X in A. I will prove X is also in what? B. So then A is a subset of B. Similarly, to prove this one, so I will take some arbitrary element X in B. I should prove X is in what? A. So this is the idea, okay, in general. So now we'll go to the proof. So here, okay, look at here. First of all, we should know R is a relation from A to B. Okay, R is a relation from A to B, and S is a relation from B to C, or S T is a relation from C to D. Yeah, yes, C to D, C to D. Now I want to prove that T composition S, composition R is same as T composition S composition R. Okay, so now I'll take okay, I'll take some arbitrary element from the left hand side. So yeah, let us take A comma D. Let's take A comma D in the left hand side. T composition S composition R. So actually, so first here I should apply what? R, and then I should apply what? T composition S. Okay. So suppose if I take A comma D belongs to this element, from this we can tell there exists a B. There exists a B in capital B. Okay. Such that A comma this A comma B. Okay. A comma B in R. This R. Okay. And B comma D belongs to T composition S. I think it is given here. A comma D belongs to R and B comma D belongs to T composition S. And then I will take this B comma D belongs to, I will take since B comma D is an element in what? T composition S. So there exists a C in capital C such that B comma C, B, this is a bracket, B comma C, small c belongs to in S. Okay, in S. Okay, S. And C comma D, C comma D in where? T. Okay. Now you can see A comma B in R, B comma C in S, C comma D in what? T. So A comma B in R, B comma C is in S, C comma D in what? T. So now I'll write, okay, A comma B in R, comma B comma C is in S, comma C comma D in T. So now from these two you have A comma C is an element of what? First you should apply R and then should apply what? S. So S composition R, comma C comma D in where? Belongs to T. Now this implies first next A comma C comma D means A comma D, okay, is an element of, first you should apply what? Second you are applying T. So second means T is coming here. First you are applying what? S composition R. So I took an arbitrary element here. Okay, let's see here. A comma D belongs to T composition S within bracket composition R. The same element A comma D belongs to T composition bracket S composition R. So this implies this is considered, this is A, totally this is A, this is B. So but A is a subset of what? B. So what is A here? T composition S composition R is A, capital A, subset of T composition S composition R. So this is the first part. So similarly, you should take an element, arbitrary element, the right hand side, and it will prove that is in the left hand side. So that is I will explain in the PDF itself. So A comma D belongs to now the right hand side. What is the right hand side? T composition S composition R. So T composition S composition R. Okay, now there exists a C in C, okay, because S composition R. Okay, there exists a small c belongs to capital C, such that A comma C is in S composition R, comma, and then C comma D in where? T. Now, from this, A comma C belongs to S composition R. Using this, there exists a B, there exists a small b in capital B. This is such that A comma B is an element of capital R, this R, and this B comma C, this B comma C is element of this S, and C comma D belongs to what? Capital T. Now A comma B belongs to R, B comma C belongs to S, C comma D belongs to T. Now I will take these two. A comma B belongs to R and B comma D, B comma C and C comma D, you will get directly, you can write what? B comma D belongs to, first you are applying what? S. So the S is coming here. Second you are applying what? T. Okay, so T composition S. Now from these two, A comma B, here B comma D, now A comma D. First you are applying what? R, that is coming here. Second you are applying this one. So T composition S is coming here. So A comma D belongs to T composition S, composition R. So I'll take A comma D belongs to T composition S composition R. I prove the same thing, same element A comma D belongs to T composition S and then composition R. Now this is a subset of this one. So it is written here. Now from 1 and 2, 1 means what? Already I told that this is 1. Okay, 2 is this. We conclude that T composition S composition R is same as T composition S composition R. Okay, second theorem. Let ABC be sets. R is a relation from A to B, and S is a relation from B to C. Okay, I'll write. Okay, S is R is relation from A to B. R is a relation from A to B. S is a relation from B to C. Okay, then I need to prove S composition R whole inverse is equal to R inverse composition S inverse. R inverse composition S inverse. Okay. So now, what is the meaning of S composition R? First, you should know S composition R means first you should apply R. So A to B and then B to C means A to C. Okay, and then from this S composition R whole inverse means what? S composition R is from A to C means its inverse is from where? C to A. Similarly, what is R inverse? Is a function from R is a function from A to B means it is a function from B to A, and then S inverse is a function from C to B. Now C to B. So now R inverse composition S inverse. First S you should apply S inverse. So C to B, and then you should apply R inverse B to A. So C to B, B to A means this is also what? C to A. Okay. Now I think this is the left hand side. This is the right hand side. So now, okay, if both the left hand side and the right hand side uh, functions are here. Here, what the domain and the codomains of the left hand side and right hand side are same. You can check it. C to A. This is also what? C to A. This is also what? C to A. Okay. Now it is meaningful to say both of them are what? Equal. Okay, now the same idea. This is considered this is A, this is B. I want to prove what? A is a subset of B and then B is a subset of A. So how they are going to do? So let us take C comma A belongs to, let us take C comma A in S composition R whole inverse. Because S composition R inverse is a function from C to A, that's why I'll take what? C comma A. Okay. Now, this implies A comma C is an element in where? Is an element in S composition R. Okay. This implies there exists a B in capital B such that A comma B in where? A comma B in R. Okay, R like it is in R. A comma B in this R. And then B comma C belongs to where? In S. So from this implies B comma A in R inverse and C comma B in where? S inverse. Okay, now I want to show that the same C comma A belongs to where? On the right hand side, R inverse composition S inverse. So I'll start from C to B and then B to A. So that this implies T comma A. Okay, first you are applying what? S inverse. So that's why I'll write S inverse here. Second, you are applying what? R inverse. Okay, first you are applying C to B, okay, and then B to A. So the same element C comma A is element of the right hand side. What is the right hand side? R inverse composition what? S inverse. So this implies we conclude that S composition R whole inverse S composition R whole inverse is a subset of R inverse composition S inverse. So this is equation number 1. So now I'll go to the PDF. Okay, so you can see here S composition R whole inverse is a subset of what? R inverse composition S inverse. Next, the other way, I should take element from the right hand side. So again, I'll take an element C comma A. So you can see I already told that R inverse composition S inverse is also a function from where? Is a function from C to A. So we can take any element is of the form what? C comma A. C comma A. Okay, so that's why I'll take an element C comma A belongs to where? R inverse composition S inverse. Now we know that R inverse is a function from where to where? So B to A. R inverse is a function from B to A. So that's why. So there exists a B in B. Okay, C comma B in S inverse. You can check it. C comma B. C comma B is in what? S inverse. Okay, and then B comma A is in what? R inverse. And then B comma A. C comma B. This C comma B is in what? S inverse. And then this B and this A in where? R inverse. R inverse is a function from where? B to A. R inverse is a function from B to A. Okay. Now, C comma B in S inverse now, B comma C is in what? S. Similarly, B comma A is in R inverse now, A comma B is in what? R. Now, again, first I apply this one, apply R, and then apply S. So A comma B in R, B comma C in S means A comma C is in what? Because you are applying R first, so R is here and S is here. The S composition R. So C composition C comma B. A comma C in S composition R means C comma A belongs to S composition R whole inverse. So I took C comma A in where? R inverse composition S inverse. Finally, I proved C comma A belongs to S composition R whole inverse. So this implies this is a subset of this. So R inverse composition S inverse is a subset of S composition R whole inverse from 1 and 2. Both of them are equal. Okay. I think theorems are over. Now I'll go to the. I think this matrix. Okay, you know that already we defined. So they gave the relation means how to find the matrix. The two elements are related. It is 1. And the two elements are not related means what? You put what? 0. So these are things you know that. And R inverse is the inverse relation of what? R. How to find the inverse relation? MR inverse. MR inverse. You should write like this. MR inverse. Okay. MR inverse is same as MR transpose. MR transpose. So MR transpose is what? Transpose of the matrix MR. Okay. Next, yes, here you can see here. This is actually the last step. This is the Venkatraman notation. So S composition R. Okay, in S composition R, he is applying R first. That's why he is writing what? MR here. And then composition what? MS. But in the Virarajan book, MS composition R is what? First he will write MS and then composition what? MR. So that is the difference. So this snapshot I took from Venkatraman book. So this is MR, this is MS, means MR composition MS. Okay, MR composition MS as per Venkatraman book is already I told to you what is given actually yes, MS composition R, I think. Yes, MS composition R. MS composition R is equal to first he is using what? R. Okay. So MR is here. Okay. And then composition is second he is applying what? MS. So you should write the matrices and then you know how to find the composition. Take the first row and the first column is like a matrix multiplication. Okay, you can get it. Okay, you can check it. So first row, I'll explain you. If you take this row and this column means 1 into 0. Okay, 1 into 0 what? First, okay, I can't write here. Okay, 1 into 0 is 0, and then R, 0, 1 means 0. Okay, R. And the third element, one meet 0 is what? 0, and then R. 3 elements are over. Fourth element, 1 and 1. 1 and 1 is 1, R. And then 0 and 1 is 0. Okay. So finally, this is equal to what? 1. So this position is 1. You can see here, this position is 1. Similarly, you can find the remaining elements. Okay. Now, okay, you can see here. So A equal to 1, 2, 3, 4. R is this relation and S is this relation. S is relation on A. Find the S composition R. So this is the usual way to find the S composition R. First, you are applying what? R, and then first you are applying R, and then next you are applying what? S. So here you should write a 1, 2, 3, 4, this given set, and then 1, 2, 3, 4, and then 1, 2, 3, 4. So 1 goes to 2, 1 goes to 2, to put arrow, 1 goes to 1, 1 goes to what? 3. Okay, similarly, you should put arrows. First from here to here R. From here to here what? You should put arrows, yes. From this 1 goes to 1, 1 goes to 3. So 1 comma 3. 1 goes to 1, 1 goes to 4, 1 comma 4. Similarly, you should write the elements. So this is the ordinary method. Now, using matrix, how to find S composition R next. So this is a matrix MR. Okay. So using this relation, you should write what? The matrix MR. Using this relation, you should write what? The matrix MS. And then we need S composition R, means M S composition R. So in S composition R, as per Venkatraman book, he is applying R first. That's why he is writing what? Here equal to is missing, equal to. So he is writing MR composition and then MS, which is equal to MR MS. Again, take this row and take this column. You should find this matrix. Okay, now this is also, this side is what? 1, 2, 3, 4. This side is 1, 2, 3, 4. So 1 comma, this position is 1 comma 1. This is what? 1 comma 3. This is 1 comma 4. This is 2 comma 1. This is what? 3 comma 3. So this is the way you can find S composition R. So in this matrix, sorry, not a matrix, but A is a set to A comma B, R is a relation, S is another relation. We need to find S composition R and R composition S and comment on your results. This is the usual method. Okay, to find the S composition R and R composition S, and comment on your result means they are not equal. So that is a comment here. And then a matrix method is also possible. First you should write what? MR, and then you should write what? MS. So MR means here AB. AB means it's a 2 by 2 matrix. So here AB, here what? AB. So AA is not there, okay, but AB is there. So AB, and then BA is also there, and then BB is there. Okay. Similarly, you can find MS. So M is composition R. M is composition R as per Venkatraman book is what? First you should write what? MR, MR, and then what? Composition MS. If you multiply MR and MS, you will get this matrix. In M, R composition S is equal to, first you should write what? MS, okay, MS and composition MR. First MS and then what? MR. If you multiply these two matrices, you will get this answer. From this matrix, you can write what? This is element A, comma B, B, comma A, B, comma B. From this, the A, comma A is not 0. So A, comma B, this is B, comma A, this is B, comma B. So these are the some of the problems. Okay. So please go through it. And this is not that much important. So interested students, please work out these problems. But I gave the solutions here. Okay. You can check it. And again, these are the some of the problems 3, 4, 5. For this problem, I gave immediately I gave solutions. So here A is a set, R is a relation, S is a relation. Question is 1, comma 3 in R composition R? Is one R 4, comma 3 in what? S composition R? So similarly, they are asking. The answer is here. A, B, C, D. For everything, I gave the answer. Okay. And next problem. For third, fourth, fifth problem, I gave the answer. This is the third, fourth, this is the fifth. Fifth problem answer for only for R composition R they gave. This is R composition, again composition R. This is nothing but one more composition. So that means what? MR, R composition R means MR composition MR. R composition R means you should put 3 times MR. MR composition MR composition MR. But answer is only for here MR composition R is here. Okay, next concept, equivalence relation. I'll check the time and then. Okay, now time is 8:10. Okay, I'll stop here. So equivalence relation is the next concept. Okay, the important concept we will discuss tomorrow. Maybe I will share the timing tomorrow morning. Okay, in the WhatsApp group. Thank you. If you have any doubts, you can ask to me. Otherwise, we will meet tomorrow. Okay, thank you.